It's great to be with all of you. Everyone have a good day? Yeah, amazing day, great organization. We have high standards for Switzerland. If a session runs a minute late, Philippe and Catherine, you're going to hear about it. But thanks so much for inviting me and for putting on an amazing conference. It's also a chance for me to pay tribute to some of my professors who are in the audience. John Abel, 1994, numerical methods, CEE 241, 30 years ago. Sergio Pellegrino, structural morphology, 1998, 99. Dynamic relaxation of an Easler shell. You passed me. Before that, Guy Nordenson at Princeton, 97 maybe, so it's great to be with my professors. And we're all part of this tradition of a community learning from each other and, frankly, trying to make the built environment better. And we all know we have a good message. We all know this work is important. And for me, IASS is the very best conference. It's the only one I want to go to every single year. Don't you guys agree? It's the only one. For me, it's really the one I want to go to every single year. I went to Melbourne last year. How many were in Melbourne last year? Raise your hand. Of those hands raised, how many of you were in Kresge Auditorium in 2018 for IASS at MIT? All right, a handful of you. Okay, well, it's great to get the band back together again. So good to see you all. I did give a keynote at MIT in 2018, which, frankly, after my time, this just feels incredibly nepotistic that I'm speaking at MIT and now my former students invite me to speak here. But while we were under this shell at MIT, we talked about some things. So for those of you there, I just want to briefly remind you in the first couple minutes. One was the work of the Guastavino family. This is a doubly curved shell, about 10 centimeters thick, and it's on the order of 25-meter span. It's unreinforced. It was abandoned with no maintenance for about 30 years, and it stood. And how many of us would feel confident to do an unreinforced shell on this scale today? Oh, and it was built with minimal formwork. So block. And since we were together in 2018, this was in my presentation, I'm very, very happy to say it's been restored. This is great. So we're raising awareness. We're raising awareness of historical structures before they're torn down. We're raising knowledge to help preserve them and to show that you don't actually need to cover this with a mat of steel reinforcing to make sure it's there for another 100 years. And we've also done a few other things. We just recently built a sculpture with free-spanning brick around a guiding cage in the Hudson Valley at Storm King. Laura Davis will present that on Tuesday afternoon, so I won't say much more about it, but it was a really cool project, and we learned a lot from it. And David Billington could never give a talk without showing Saugina Tobel Bridge. He was my professor, and Saugina is always there. My Saugina Tobel is, of course, this staircase by Guastavino, doubly curved, no steel. The builder, Rafael Guastavino Jr., dropped out of education at age 10, formal education. The nerve of this guy to build this with no computer model, no nonlinear analysis, no dynamic analysis, and then to add insult to injury, this is in the civil engineering department at Carnegie Mellon. So you have generations of students going up and down the staircase without the foggiest idea how to calculate that it works, and it has no steel. This is 1914. Now, since we were together at MIT, I realized this staircase was proposed in 1914. The difference, this one was actually built. This one then became the only possible way to build for the next 110 years. And the only possible way to build a staircase is this. So I ask you, is this the pinnacle of all time? And 100 years from now, is this what the building code should say is the only way to build a staircase? And this recognition that we are following a culture, our building codes have culture, our system has ingrained ways of doing things, and we're at a time in the world where there's so many assumptions that we have to question when we look at the climate crisis, when we look at inequality, when we look at who benefits from our projects. So I want you to think about what someone with a 5th grade formal education did here, and that was not mentioned in publications. It was not an important structure at the time, but of course, this was an important structure. So let's think about that. So one key message from 6 years ago and still today is beware of progress ideology. John Abel remembers my undergraduate thesis with this Inca grass bridge in Peru. We were load testing the cables, and this bridge, I still believe, has more to teach us than the iron bridge at Colebrookdale, which is always in historic structures. This bridge has been built by the same 4 communities for 700 years, speaking an indigenous language, and every year the bridge grows on the hillside, it falls into the river, and it's washed away by the river. And when they build it, they drink a local beer that's made from the local corn. Find a more sustainable structure than that. 700 years, local beer, local grass. I know what you're all thinking, it's some really good grass. So, for those of you who were with me in Kresge Auditorium 6 years ago, these were the 4 key conclusions: that we should study history. It's fertile ground for designers. If you're in music or literature or art or architecture, we're constantly learning from history. Structural engineering, structural design is not studying enough of our history. We have new design tools that can help us bridge the gap, help design teams explore, and we need to really think about traditional materials to create ultra-low carbon buildings and perhaps redefine progress in the 21st century and not base it on that 1914 staircase filled with steel as the only possible way to build a staircase. And now we're in Switzerland. How spectacular is this? I don't know what you all did yesterday, but I was lucky enough to take a bus to this gorge and go for a hike with the great Swiss designer Jörg Konzett and to see some of his footbridges. I highly recommend this, Under the Men Bridge. So the Swiss tradition of structural design is alive and well. It's known around the world, so it's especially nice to be here in Zurich. And boy, there are a lot of cool structures to look at. So things are looking up here. But we were also, many of us were influenced by Billington's work on the Swiss legacy in an art exhibition that highlighted the work of Heinz Isler, of course, as the great shell builder, but also Maillard, Min, and Ottmar Ammann. And Maillard, of course, is super well known as this great disciplined and playful designer. Here he is allowing the ash to go as far as possible without falling off. So he's got to hold very, very still. So it's a playful moment, but it's also quite disciplined, what you need to be a designer. And of course, some of you and the students in the audience especially, of course, know Sauginatobu. You may know the Schwanbach Bridge with this incredibly curved, thin deck, well known around the world. I can't help but also add on the 85th anniversary, the 1939 cement hall of a mature Maillard, to give you an idea of how far ahead he was in thinking about surfaces and what was possible in shells. This is built in Zurich as a pavilion. The shell is 6 centimeters thick, not very much published at the time, kind of unremarkable in the press. And look at the cleverness of the formwork. It was gunnited onto the shell. And also look at all of the elements that are integrated here. You have shaping according to where you need greater bending. You have lightening of the slab and allowing in natural light. And just a radical, radical way of combining different elements. So if someone were presenting this project at this year's IASS, we would say, wow, that's a pretty impressive shell. Oh, and he calculated this on about 1 sheet of paper. So this is what it looks like in section, with adding some parabolas, of course, but then changing curvature a bit to stiffen it. And the way he conceived of it was essentially as a deep beam inclined. Calculate that very easily on one sheet of paper. It's supporting a series of arches and then cantilevers coming off of that. So radical structure in a synthetic way by a brilliant designer at the end of his life. This gives you a better sense of the geometry. So I pay homage to this shell here in Zurich because it was so important for our field. And here he is in the center as they're trying to bring down the temporary shell with dynamite. Of course, you all know what happens. They put the dynamite, they blast it, and the shell stands. And they do it again and it stands. So they eventually have to pull it with a bulldozer to bring down the shell. Incredible strength through geometry, 6 centimeters thick. And here he is, just a year or two before he dies, picking through the rubble, studying, being a student until the end, and thinking about what he can learn from this integrated design. And he's absolutely projecting into the future what could be done with shells. But again, wasn't paid much attention to at the time. Of course, Eisler goes on to do remarkable things with hanging geometries that are compression only. If you have a chance to go and see the Sikli building in Geneva, it has the Candela exhibition now, which is super exciting. So I hope some of you are able to go and see that. And this is an image from Billington, which shows Eisler standing on Sikli and pointing to the unlimited future of shells. We're all on the same page? Good. But I also have to pay homage here at ETH to something that inspired so many of us, and that is form finding and exploration of geometry through graphic statics. And we're delighted to see all of the renaissance of graphic statics happening around the world, and a lot of it being led here at ETH as well. But we pay homage to these professors, and this important work you can constantly continue to learn from. But I also want to highlight Maurice Kakelin, one of the students. We've recently been digging into some of his work, and of course, many of you know that this is Kakelin's original drawing of a tower or a pylon that would have no force in the diagonals. So there's a very subtle message here, which is that the Eiffel Tower is actually Swiss. And the key thing, with all due respect to our French colleagues, the other key thing, of course, we've recently been digging into archives and the design process of this, one of the greatest bridges, the Garbi Viaduct, Maurice Kakelin also designed using graphic statics that he learned here at ETH. And we've got some exciting new results on that we're going to present at next year's IASS. So I'm not going to go into a lot of detail, but I do have a very serious message for all the students, which is you must go and visit great structures and learn from them. Study them, climb on them. You can learn so much from visiting built buildings. Don't you think, Philippe? 20 years ago this summer, we made a pilgrimage to Garbi Viaduct. We're still learning from it. That was back when I had so much hair. And so here in Zurich, I pay homage to the Swiss legacy that Billington writes about in The Tower and the Bridge. We could quibble with some things in it, but a lot of it still holds and holds well. And for those of you who didn't have a chance to hear Billington lecture, he always spoke about the 3 E's of structural design, in particular efficiency, economy, and elegance. And the idea is just so simple. We obviously must build efficient structures from a material standpoint, but they must be economical to build, or else they're wasting those natural resources. And ultimately, as Maillard said, we are seeking to avoid ugliness. So within those constraints of efficiency and economy, we're trying to find elegant solutions. So these 3 E's, I think, still hold very, very well for structural design. And yet, somehow, I think of them as quite 19th and 20th century in a way. And here we are in the 21st century with a whole set of other problems. So these are given. Now what do we have to think about? 20 years ago in this book on Dieste, I had an essay where I proposed a 4th E, environment, thinking about environmental implications of what we build, and also what's appropriate. For those of you who know Dieste's work, in the context of Uruguay, local builders, hollow, locally made bricks, light shells, he's really thinking about that context. And I published this in an essay titled Eladio Dieste as Structural Artist, and Billington got very upset with me because I said there's a fourth E in structural art, and it's environment. He said, oh, no, the 3 E's are perfect. We don't need other new ones. And here we are 20 years later, and I'm still going to say environment has to be a consideration that we need to constantly bring into our work. And I think you all know our challenges, that we're on the order of something like the floor area of one Chicago to be built every 2 weeks for the next few decades. And we're following that 1914 reinforced staircase as the only possible way to build. So most of the buildings are, and of course, we're doing this while keeping more CO2 in the ground, because we're at 420 parts per million and climbing with absolutely no hope of slowing down anytime soon. So how are we going to build a Chicago every 2 weeks while putting more CO2 in the ground? We need IASS. We need new ideas. They need to work with all those constraints of economy and efficiency, but they also have to really think carefully about context and environment. And in particular, with all due respect to Switzerland and Canada and the UK, wealthy countries with lots of water are probably going to be okay. Most of the floor area that's being built is in Africa, India, Latin America. If you look at existing floor area and what is projected to be built, most of it is going to be built not necessarily in Switzerland or Canada. And if we ask ourselves, how can we most easily avoid a ton of carbon emissions, we may have better opportunities collaborating with colleagues all around the world. And so it's so great that IASS is so global, but I'd like to really shine a light on where the needs are to not import steel and cement and build inefficient structures. And then if we can win in the marketplace, we can have a really big impact here. And of course, some of our work on low carbon floor slabs, these 2 digitally fabricated here from BRG, and my rather ancient methods of Guastavino tile construction, an Islamic construction method from more than 1,000 years ago, unreinforced shells, doubly curved floor systems. We were saying this 8 years ago that this is important, and I want to highlight another paper we'll have tomorrow. Nebu is presenting on some low-carbon vaulted floors, and we'll be building a prototype in Ethiopia next year. And these are about half the cost and half the carbon of existing concrete slabs in low-cost housing in Ethiopia. So we're working with builders to see, can we create projects that are going to win in the marketplace, and then the low carbon just becomes a bonus. And of course, the Mapungubwe project, this is lost form work for a concrete slab on the left, but we think there are constantly things we can learn. So we're still on the same bandwagon 15 years later. Unreinforced shells with low strength, these are about 1 megapascal shells that have the potential to build low-cost structures. I also want to remind everyone, for those of you who were here in Venice in 2007, I distinctly remember the great structural designer Jörg Schleich got extremely upset about this structure at an IASS conference. Does anyone else remember that? You remember, good. I'm not the only person here who remembers that. He was really upset about the lack of efficiency, the wastage of materials, and that had a big influence on me as a young professor. And so that was one of the ideas I said to Catherine maybe more than a decade ago, and then I got out of her way. And so I again pay homage to Schleich and him demanding a higher moral and ethical responsibility from design teams with this colossal structure as an example, not to be followed. So Catherine quantified over a ton of CO2 per square meter. The London Olympic Stadium, 4 years later, is 1/5 of that per square meter. So you can build about 5 London Olympic stadiums for 1 bird's nest. And then the Mapungubwe is a factor of 4 again below. So local materials, unreinforced, you can go dramatically lower carbon. And so this was work we published about a decade ago. But I also want to highlight another topic that really weighs on me today. When I gave that talk in 2018 at MIT, since then, Wikipedia has created a category titled Sports Venues Demolished in 2018. You don't even want to see 2019, 2020, 2021, 22, and 23. It's getting worse. So we put a lot of resources, a lot of talented design teams build structures, and then they're torn down within 20 or 30 years. And we all can think of examples, whether it's the King Dome or other examples that you see here. But this also raises a question about the lifetime of our structures and really thinking about many of our structures almost like disposable food containers that have short lifetimes, and we need to really think about minimizing them. And if you look at a typical scrap heap, metal scrap heap, you might find steel beams like this at the edge that are holding the mountain of steel scrap in place. Well, I have a crazy idea. Actually, Juliana and many of you here have this idea, not just me, that these steel beams could do more than just retain that scrap. We could use them in new projects. And we need to change our supply chain to acknowledge that when buildings come down, we should mine those resources and use them in new projects. And I know a lot of you are here working on those topics, but for me, that's super exciting. And we'll present some work that has implications for steel reuse on Wednesday afternoon. And since 2018, when we were together at MIT, some of these ridiculous towers have been built in Manhattan. Now, typical tall building, aspect ratio. If we were so lucky to have the engineer of the tallest building in the world here today, he would tell us the aspect ratio should be 1 to 9, 8 to 1, maybe even 7 to 1. Bill?
In steel, 7 to 1. In concrete, 8 to 1.
Okay, 8 to 1 in concrete, 9, what'd you say, sorry?
7 to 1 in steel.
7 to 1 in steel, 8 to 1 in concrete. Take it to the bank. From Bill Baker. What do we have here? 25 to 1, 15 to 1, 27 to 1. Obviously on the hard bedrock, the Manhattan schist that you can do there. But why are these projects being built? Here's 432 Park Avenue. We've been looking into these structures and quantifying their material. Oh, I got some great news. The penthouse is now available. I pulled this off Zillow today. Every single floor is one apartment for one oligarch who's looking to bank money. And so that's why the project is built. It's for that floor. Now, here are the material quantities in terms of global warming potential, kilograms of CO2. On the far right is 432 Park, that concrete building. These are other tall buildings around the world. 432 Park is 425 meters tall. The Sears Tower, the artist formerly known as the Sears Tower, the Willis Tower, is around the same order of magnitude. It's 1/5 the carbon. The Burj Khalifa, 1/3 of the carbon and twice the height. Shocking. Absolutely shocking. And yet, these projects are built with huge amounts of material because there's a design team who said this is a good idea. Or I'm happy to take my paycheck for this project. So I'll add a 50, ethics. What are we doing as designers? What projects are we working on? All our fancy education, our dynamic analysis, who benefits from our work? And why? So I know I live in my ivory tower in the university. I seem to be just creating other professors there are a lot of us. But we have an obligation to talk about this, to talk about ethics. And so I'll ask a few basic questions. Should the project be built at all? Who benefits from this project being built? And should I personally work on this project? Because I do think we as a community can start to take a stand that there are certain projects, as Schleich reminded us in 2007 in Venice, that the bird's nest was a disaster. And he would not have worked on that project. Or he would have tried to make it a lot better and then may have walked away. So, and then, I'm sorry, Professor Billington, I'm going to add a sixth E. Education. Our curriculum right now looks like 1952. And what do I mean by that? Every project is a new building on a greenfield site, and we're going to follow the concrete code, and everything will be okay. Another Swiss person said, we can't solve problems using the same kind of thinking we used when we created them. And that's where we are right now with the climate crisis and with global inequality. And yet our curriculum is not evolving. What happens in the university? It's not quite this bad, but it's pretty close. Here's my main gripe with what we're doing right now. Problem after problem after problem in the education of engineers has one single answer. One answer. It's really, really nice because then when you give a test, you can grade the test quickly and there's always one right answer. But boy, the world is much more complex than that. And we need designers who can bring many more options to the table. And so I would like to see our curriculum evolve radically. Catherine embarrassed me, so now I'll embarrass her. I think this is what the classroom should look like. Building things. Someone agrees with me. Yeah, one person? Two? Okay. So this is what a classroom could look like. Let's think about hands-on learning that is open-ended, that brings together different disciplines. We can learn from each other. And so for me, I really like to see more radical redesign, especially of structural education. We need more open-ended design, much more collaborative and interdisciplinary, and we need way more emphasis on existing structures, depending on where you are. But in North America, about half of all spending is on existing structures in construction. And yet in our curriculum, it barely exists. And in Europe, it may be even more because of your built heritage. So that's what I'd love to see. And so the main thing I'm working on right now is trying to change an undergraduate engineering education at MIT to have much more open-ended design. So we're doing an adaptive reuse of a large brick warehouse. And these are going to be design studios with hands-on making projects, bringing teams together to work on pressing challenges with collaborators from around the world. And our hope is that we're going to be able to change what an engineering education looks like to have much more creative hands-on. I also want to highlight our students going out into the world and taking ideas. So if you come from Paris and you're concerned about urban heat island effect, don't wring your hands, create a startup. And Roofscapes is now making real change in Paris, so that's very exciting. And or build some low carbon floor systems that can compete in the market. Special thank you to our sponsors, Vaulted. And that's a seventh E, entrepreneurship. Because we have to take our ideas and we have to take them out in the world and they have to win in the marketplace. Because if they live on a shelf as a thesis and create a new professor, that's probably okay. But the world doesn't actually need more publications right now. The world needs better ideas and better ways to build. So even though I was very embarrassed to be invited by my former students, they asked me to kick things off with a challenge for all of us. And so here it is. While efficiency, economy, and elegance are powerful historical examples, environment, ethics, and entrepreneurship are just as critical for the future. Those first elements we can take as a given. And we need radical transformation in education and how we teach students and how students learn. Let's not call it teaching. Let's how people learn. And so the people on the planet demand better buildings. And with 5 seconds left of my 30 minutes, IAS can lead the way. ISS, thank you so much. No problem.